Hi. So the next unit we're going to be studying is about energy resources. And even though what I'm going to talk about in this screencast isn't covered in the course exam description document itself, it's pretty important information, especially if you've never had a physics class. So let's get into it. Let's talk about what energy actually is. Well, it turns out it's hard to say what energy is. It really sort of it eludes definition. But the best we can do is say energy is the ability to do physical work. Okay, to move things, heat things up. All right, but here's the thing: it might be hard to define what energy is, but it's easy to recognize it and to measure it. So energy takes a lot of forms that we're familiar with: an object moving, something being hot, something having making sound, something giving off light. Something transmitting electricity. These are all forms of energy. So it takes lots of different forms, which is what makes it a little bit confusing at times. But regardless of which form, all forms of energy can be measured in a unit called joules. We're not going to worry in this class what the definition of a joule is. It doesn't matter. But energy is measured in joules and, or kilojoules, whatever, megajoules. All right. Now, the thing you do need to know for this course, though, and this comes up a bit, and sometimes it's asked directly about on the APES exam, and that is the first two laws of thermodynamics, because they play an important role in many aspects of environmental science. So the first law of thermodynamics, and we've talked about these before, is pretty easy to understand, and it basically is what's called a conservation law. It says that you can't create or destroy this. So energy is conserved, meaning you cannot create or destroy energy. That's the first law of thermodynamics. You can transfer it from one object to another, from the sun to the ground. You can change it from one form to another, from light to heat, but you can never create or destroy it. However much you start with is the amount you end up with, always. Right? There's never any energy that is just lost. I mean, when we talk about loss, what we really mean is it got converted to heat, which is hard to use. But let's just look at an example here. Okay, ready? I've got this awesome toy car I drew for you. What an artist I am, okay? Now, this toy car has a battery, and this battery has 10 joules of energy stored as potential energy inside this battery. The car is at rest. It has no motion energy at this point. Okay. Now, I use remote control to turn it on. Now, what the first law of thermodynamics tells me is after this car starts moving, now it has 3 joules of energy of motion, and it's giving off 2 joules of heat energy. That's a total of 5 joules. Well, then there must be 5 joules still left in that battery because the total is always going to be the same. 10 joules I started with, 10 joules I end up with. Some of it got converted to motion energy, some of it got converted to heat energy, some of it remained as potential energy, as chemical energy. However, none of it was destroyed, and none of it came from elsewhere. If I add all this up and I come with 11, I'd have some explaining to do, okay? Or if I add it all up, I come with 9, it's like, well, where's the other one? Because you can't create or destroy it. But now let's talk about the second law of thermodynamics. This is probably more important in apes because this is sort of the driving idea behind food pyramids. This is why energy is dissipated as we move up a food pyramid. So remember, it's not destroyed; it just gets dissipated. So the second law of thermodynamics tells us this: anytime energy changes form from light to heat, okay, from electricity to sound, or is transferred from one object to another, from the sun to the earth, from a battery to a car, that some of it is always, always, always converted to heat energy. And heat energy is just the random motion of atoms, okay? So you cannot have 100% transfer of energy from one form to another without generating some heat in the process. So this first diagram I drew here is just not possible. You can't start off with 10 joules of energy stored in a battery of a toy car that's not moving and end up with 10 joules of energy in the car moving and no joules of energy in that battery because some of it is always going to end up with heat. This is not possible. We would call this 100% efficiency. My target energy was motion, and I turned all of this into what I wanted. Never going to happen. Okay. Instead, what's going to happen is some of it is always going to get converted to heat in this process. So what is possible is I start off with 10 joules in a car that's not moving. Afterwards, I drain the battery. There's no more joules left here. Well, where do they go? Well, 8 of them went into moving the car, but 2 of them went into heat. All right. And the thing about heat energy is it's like wasted energy in most cases because it's very difficult technologically to do anything with heat energy other than stay warm. There are ways of using it, but it's tricky and limited. Now, efficiency is going to be an important thing in trying to understand energy resources. This could be our developing better efficiencies is something that engineers have been chasing for my whole lifetime, and it really is buying us a lot of a breathing room in terms of the time period in which we'll run out of our energy resources. So efficiency is basically uh, basically the percent of energy that ended up as your target or intended energy. So what you do is you simply say, what is the target energy or intended energy? In the case of that toy car, it was motion energy. Okay, divided by the amount of energy that had to be expended to make that happen, or the maybe the starting energy and the finishing energy, right? Times 100 to get a percent. So let's just look at an example, and that'll make sense. I know right now it's kind of confusing. I'm sorry I didn't explain that great. Okay, so here you go. Start off with a car. It has 400 joules of chemical energy stored in gasoline in its gas tank. Okay, and then what happens is, uh, I turn the car on, I press the gas, I just go faster, 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 and then I end up running out of gasoline. And what I find is that you know what, I only got 100 joules of motion energy out of the car. The other 300, they went into making the engine hot and to making the car loud. Okay, I accidentally generated heat. I accidentally generated sound, which got converted into heat. So what's my efficiency? Well, what I'd say is like my target energy, my intended energy was motion energy. I got 100 joules of that. How much energy do I have to expend to do that? 400 joules of gasoline. So that means only 25% of the energy ended up where I'm meant to go. And here's the thing about cars. If you've ever touched a car engine, they're hot. Cars have pretty low efficiencies, typically less than 30%. So that means of all the energy we release on the roads, like only a quarter of it, a little bit more, is actually going to where we want it to go, and the rest of it's just wasted. It's just making our cars hot when we don't want it to be hot. So you see, efficiency is going to be an important concept. Now, understanding energy, it really helps if you can learn to just see how it manifests itself, how it appears to us. Okay, so let's just real quickly go through this. Energy basically takes two forms. It can take energy of motion form, or it can take the form of energy of position. So energy of motion, which we call kinetic energy, uh, it can take different forms. So it can be like an object moving, like a baseball moving in the air, a car moving down the street. It can take the form of heat, which is really just random moving atoms. So if you touch a stove and it's cold, the atoms are moving slow. They don't have much kinetic energy. But if you touch it and it's hot, it's because the atoms are moving really fast. So they had more energy of motion, but they weren't going anywhere. They're just moving randomly. Light energy is a little bit harder to understand. It's a whole topic of its own. But basically, it's you can think of it as it's just photons or waves, whichever you prefer. We'll think of it in terms of photons, which are little bullets of light, packets of light energy that are traveling, say, from the sun to the earth or from a light bulb to your eyes. Sound energy is just the back and forth movement of matter that basically is how I'm wiggling my vocal cords. It's making the air move. So there's kinetic energy there, and that's making this microphone pick this up and making your ears wiggle. Okay, your eardrums wiggle. And then electricity is the movement of electrons through wires, or maybe ions through nerves, okay, or muscles. Now, energy of position we call potential energy. And this is what's really important, because the history of humanity is all about uh, uh, getting possession of potential energy and then releasing it where you want to. Okay, so energy of position can take different forms. Potential energy. The three main forms it takes are gravitational potential energy. A rock up high is in a high energy position. So if it falls down, it releases that energy and converts it to kinetic energy. I have 100 joules here, and when it reaches the ground, there's 100 joules really. Now, some of it's going to be heat, so maybe 99 joules of kinetic energy and a joule of heat energy. Okay. Chemical potential energy, is energy stored in the electrons and the bonds between atoms. So the compound nitroglycerin. It's like the sort of active ingredient of dynamite. Okay, so you have this complex molecule has a lot of energy stored in the bonds, okay, especially between the nitrogen and the oxygen. And then when I detonate it, I'm rearranging that nitroglycerin molecule into these less energetic carbon dioxide and water and nitrogen molecules, and so that the leftover energy manifests itself. It can't be destroyed, so it turns up as sound and heat and light. And then there's nuclear potential energy. So nuclear potential energy is energy that's stored not in the bonds between atoms, but in the bonds between nucleons, between the particles that make up a nucleus, the neutrons and the protons. And so technologically, in the 20th century, people learned that you could split big atoms, and then when you do that, there's less nuclear potential energy in the smaller nuclei that you produce. And so that leftover energy can't be destroyed, so it shows up as heat or light in the case of an atomic bomb. But the other thing is like the sun is also powered by nuclear potential energy. But instead, if you take hydrogen and put together to make helium, element two, turns out there is a lot less potential energy there in that form. So that decrease in potential energy means that energy has to go somewhere, and it gets converted to heat and then to light, and then comes to Earth in that form. And by the way, throughout my lifetime, people have been trying desperately to figure out how to make that type of energy happen, that fusion energy happen on Earth, and they're still pursuing it. And they've been making some gains, but it's been a slow go. All right, so those are the forms of energy. All right, let's just kind of walk through this here. So one thing I do think is worth noting, I think it's just a cool thing to know, is that almost all the energy that we encounter on Earth, uh, apart from nuclear power, really, it comes from the sun. All right, so let's just look at this. All right, so nuclear reactions in the sun convert nuclear potential energy into heat. That heat gets converted into light, and those photons of light stream out of the sun and they come to the Earth. Now, when those photons get absorbed by the ground, they can't be just that energy they're carrying can't be destroyed. It has to be converted into something, and it turns out it gets converted into heat energy. The ground gets warm. All right. So if 100 joules of energy comes in from the sun, well, I can get 100 joules of heat energy because that's not violating the second law of thermodynamics because all of it got converted to heat. But other things could happen instead. So when I heat the ground up, well, it's going to heat the air above the ground. And when it heats the air above the ground, it's going to cause convection. Well, convection involves moving things. And now I have kinetic energy, the movement of air molecules. It makes the wind. And if I put a windmill up, I can convert the kinetic energy of the moving air into electricity, which is moving electrons. But ultimately, that sun that's coming out of a windmill, it's really solar energy, right? The energy came from the sun, hit the ground, made the ground hot, then it got converted into kinetic energy of air, which then got converted to kinetic energy of the windmill, and then it got converted into the kinetic energy of the electricity. And remember, at every step, some of it got converted to heat because of the second law of thermodynamics. Dams, hydroelectric power, is something that we'll study in this unit. And they're also solar powered because what happens is, and this isn't the best diagram, but I was just too lazy to do another one, light from the sun heats the water evaporates. It gets carried upwards, gaining potential energy, right? The water molecule in the air has more energy in it than a molecule down in the water level. Now, convection currents will carry that over here, and that now it falls down and it's releasing its potential energy and converting to kinetic energy. The rain is moving down. But if I capture it behind a dam, I have all this potential energy behind a dam, which I then release and convert back into kinetic energy. But how does the water get behind the dam? Well, the sun put it there, right? The sun lifted water out of the ocean, put it in the air, and put it behind the dam. So a dam is still a form of solar power. And so is you and so is I say so is you and me. So are you and me? We're powered by the sun as well because here's what happens: photosynthesis basically works like this. Plants during photosynthesis take carbon dioxide out of the air. They take water molecules out of the soil, or if they're aquatic plants, directly out of the water they're in. And then what they do is they absorb light from the sun, photons of energy from the sun, and they take that energy and they use it to rearrange these molecules and turn it into this molecule. Well, the arrangement of electrons here have more energy in them than the arrangement of the electrons here, so that energy that came from the sun is now stored in the bonds between these hydrogens and carbons and oxygens in a glucose molecule. All right? So this is where all the energy ended up. But that energy is basically energy that came from the sun and ended up getting stored as chemical potential energy. Now, when we release chemical potential energy by saying, I eat my breakfast or I burn a log, essentially what I'm doing is respiration, right? I'm doing the opposite. I'm taking this molecule that has a lot of chemical potential energy stored in the bonds between the carbons, the hydrogens, the oxygens. I'm using oxygen to break it apart, and I'm rearranging those bonds into lower energy bonds in carbon dioxide and water. And then that leftover energy can't be destroyed, so it has to go into some form. It can take the form of kinetic energy or heat or electricity in my nerves or whatever. Now, there are two forms of energy we encounter on Earth that do not have anything to do with the sun, but really only two, and that is geothermal energy and nuclear energy. And in both cases, those are examples of nuclear potential energy being released. So inside the Earth, the decay of heavy isotopes into more stable isotopes releases energy as the nuclear potential energy is released. And the same thing happens inside a nuclear power plant, which we will study in detail. But those are really the only two forms of energy that we use in our society that don't come from the sun. But the sun itself, remember, it is basically a giant nuclear reactor, but it's not splitting atoms, it's fusing them together. So it's taking hydrogen and turning it to helium, and in the process, it's releasing energy. All right, so thanks for listening. Sorry it took so long. How do I do this?